Oh, little Flo, I love you so, especially in your nightie. When the moonlight flits across your tits, oh Jesus Christ almighty. Greetings, the Astro 30 here with yet another kit to build. Now, this one's seen better days. It's very discoloured at the top here. It's supposed to be white. It's the KC5201, available from Jaycar, high performance power amplifier kit, and was published in the April edition of the Silicon Chip magazine in 1996. So this makes it over 20 years old. However, Jaycar no longer sell these kits in store. You can only get them online, which is exactly what I've done. It says a real powerhouse that delivers up to 175 watts RMS. Yes, the wank figure there, with very low distortion plus signal to noise ratio figures, better than any CD player. Still don't quite understand that sentence. And blah blah, spaced around Motorola, basically Japanese commercial amplifier, flat pack transistors and PA amplifiers. Nothing terribly exciting. Yeah, the packaging is a little bit worse for wear. I did see a hole in here somewhere. Maybe I was imagining that. Anyhow, it's supposed to deliver up to 175 watts RMS. Now, when I say that's a wank figure, they shouldn't really be using RMS anymore. It should be more like average power, or continuous average power, or just give us the peak power. Anyhow, the only thing with this is it's designed to run on a power supply that uses a 40 volt AC transformer up to 300 VA, which is a roughly plus minus 56 volt power rails. Now, my test environment, I cannot generate that amount of power.
Tom, how am I going to generate that kind of power? It can't be done, can it?
Maximum I can get is plus minus 30. So I'll have a look at the schematic in a minute, but I'm pretty sure it should still work on plus minus 30, but just at reduced power, obviously. So let's get the packaging open. So here's a reasonably nice printed circuit board. It's just single-sided, the usual type of material that Alltronics kits use. This is from Alltronics. You can see here we've got what's known as our star ground point. So all the earths of the input, speaker outputs, and the power output stage all comes back to a central point. Now, the performance statistics on the instruction manual says 125 watts into 8 ohms, 175 watts into 4 ohms. That's output power. Music power, well, I'm assuming by music power they're talking about the peak, which is 140 watts into 8 ohm and 230 watts into 4 ohm. So this first output power would be the RMS, the second one, music power, would be the peak power. Frequency response is negative 0.3 decibels down at 20 Hertz and 20 kilohertz, see figure 6. Input sensitivity is 1.37 volt RMS for full power into 8 ohms. Harmonic distortion is less than 0.03% from 20 Hertz to 20 kilohertz, and it's typically less than 0.003%. Signal to noise ratio is 114 decibels unweighted, 20 Hertz to 20 kilohertz, 122 decibel A-weighted. Dampen factor is greater than 95 at 100 Hertz and 1 kilohertz, greater than 50 at 10 kilohertz. Stability, unconditional. That means basically the amplifier is not going to suddenly, spontaneously go into oscillation. That's what they mean by unconditional stability. And nice, this is the first kit that I have got from from Jaycar in a long time that actually gives you the printed circuit board artwork here. I mean, this is an older kit, so it stands to reason. All the older ones I've got also come with a PCB artwork, but the newer ones don't. What is this bollocks? Plastic power. Okay, that's great. Oh yes, there's two names I'm familiar with, Leo Simpson and Bob Flynn. Now here's the schematic. Now they've actually changed it to a 115 watt power amplifier for the description. However, up here it says, for technical or modification inquiries, please contact the designers publishers at Silicon Chip Magazine. Okay. Anyhow, it's a pretty much bog standard amplifier with a current source up here for both the VBE multiplier and for the differential input stage, plus a current mirror down the bottom here. A Zobel network here. The only difference with this one is it's missing the resistor that you normally put between the capacitor and ground and output. This output stage is a complementary class A-B configuration. Q7 and Q8 here, which is basically the VAS, is basically called a cascode stage more than a VAS stage because of the way that this is configured here. And so they're saying that the output stage symmetry is actually Darlington configuration, but I cannot see... Oh yes, I see what they mean by the Darlington configuration. Duh. It's the driver to the first power output transistor and second power out transistor, because both of these power transistors are in parallel with each other and connected as a Darlington configuration on this side anyway to Q10, and Q11 to these two forms the second Darlington stage. So yes, this is the only problem with printing color in black and white, and like transistors like this all filled in grey. Kind of makes it difficult to see things sometimes. But that's the schematic. It's yeah, pretty basic. It runs on plus minus 57 volt. There is no short circuit protection other than these two 5 amp fuses. So if you short the output, it's going to blow either one of these fuses. So that'll at least somewhat protect your output stage. But yeah, this is what I never liked about power amplifiers that didn't employ some form of short circuit protection, that didn't blow the fuses on the power amp board, so you'd actually have to open the unit that it was in to replace them. Yeah, so they could have included a VI limiter in there, because with all this real estate that they've got on this PCB here, they could have actually, you know, included one. And quite frankly, this could now be redesigned to double-sided and shrunken down, and then you could include things like a VI limiter. Anyhow, that's getting beside the point here. So I guess the thing to do now is to stop talking and actually assemble this thing. So what I might do is do this in time lapse. I'm just trying to figure out what the hell do they mean by 560 ohm 5 watt. Oh, that goes across here. Couldn't see the holes. Well, that's interesting. How's that 5 watt device going to fit with the fuse holder there? Just notice that next to this fuse you've got this 560 ohm 5 watt, and there's one on the other power rail as well. So that's kind of confusing, because it would hang over the edge of the board and also be in parallel with the fuse, defeating the fuse. Okay, so maybe I need to look into the instructions on that. So here's the overlay diagram for all the components, and it's showing these in dotted lines. I think you use these two resistors during testing, i.e. when adjusting VR1 for the quiescent current. I think they want about 27 mA or something. So there's a few pages later. The 560 ohm 5 watt round resistors can also be installed at this stage. They are wired to PC stakes next to each fuse holder and are used during the setting of the quiescent current. So you put PCB pins in the holes where that 5 watt resistor is supposed to go, and then you would solder the resistor across the PCB pins, and then adjust the quiescent current and then remove them. They give you the drilling guide for the heatsink, which is nice. So probably on the last page, testing, access to a suitable appliance which is already working. We will assume that you have made or have access to a suitable power supply which is already working. I like that first opening sentence. So then when you're actually doing the quiescent current, it says monitor the voltage across one of the 560 ohm 5 watt resistors. With VR1 fully anti-clockwise, the voltage should be closer to 0 since there is no quiescent current in the output stage. Then you slowly wind up VR1 clockwise until the voltage starts to rise. Set VR1 for a voltage of 14 volt across the 560 ohm resistor. This is the equivalent to a quiescent current of 25 mA or 12.5 milliamp through each output transistor. Then you're supposed to leave the amplifier to run for 10 minutes or so. That's unloaded, just sitting idle. And then retouch the setting of VR1 if necessary. And then you finally fit the 5 amp fuses and my module is finished. However, they didn't say anything about removing the 560 ohm resistors, but, well, the fuse would basically short it out. But if the fuse ever blew, that 560 ohm resistor is now going to be in circuit, and it's still going to allow power to go to the output stage, which I believe the fuse is across the output stage. Which will then mean allowing, even if it's short-circuited for instance on the output, still allowing the short circuit to be present across the output devices and allowing power to still, and current to still flow through the output stage through that short circuit. So yeah, you would remove the 560 ohm resistors, you wouldn't leave them there, but they didn't say that, but it would have been handy if they had done that. Anyhow, I'm getting sick of talking. You're probably getting sick of listening to me. This is going to be fun to edit this intro. Anyhow, I'm going to stick this in my tool, and we're going to build this up in time lapse. I'm going to put all the components on bar the output stage transistors. So I'm going to do everything but that, because, well, I've got to get it lined up to a heatsink. And speaking of heatsink, I might as well use this one that's been knocking about for a while. That should be more than adequate, I think. So, not sure where I'm going to be putting it, but that's why I'm going to leave the transistors off so I can, work out how high to bring up the transistors when drilling. So yeah, let's get started. Okay, everything's soldered in bar the output stage. Now, a couple of problems. You may have noticed that I used some solder wick and moved a couple of these large 1 watt resistors around because I read the values incorrect and put them in the wrong spot. Second thing is I had to drill out the holes for these two transistors because they were only at 0.8 and they needed to be 1mm because otherwise the leads would not fit through. 3, the heat sinks are way too big for the area that they're crammed into, so that the fins actually come into contact with other components. This one's at a funny angle to the transistor to try and keep it away from that 100 picofarad capacitor there. So that looks pretty bad as it is, but it's functional. But I don't know why they just didn't put the correct size, you know, heatsink in, because there is one slightly narrower than that, which is what it should have been. But if it annoys me, I'll change it later. Other than that, the other hardest issue was trying to get the inductor to solder properly, because the enamel on the copper wire there was being a pain. And this inductor's been sitting around a long time. The tape was even coming off of the bobbin there. Some of these components have been sitting around a long time in these cardboard runner things. There is a technical name for that, I can't remember what it is offhand. Tag strip. And of course it's just like brittle as anything when you pull them out off the cardboard, because I don't know how old this kit actually is, but it's been sitting around a long time. In fact, that resistor there looks sun damaged, discoloured. It's gone sort of a yellowy green instead of a blue, which is what it's supposed to be. Anyhow, now next stage to do would be to build the output stage. And that would be involving drilling the heatsink first. So after all this effort and time, I hope that this thing works when I first power it on. Well, at least at 30 volt plus minus, of course. It's designed for plus minus 57. But yeah, that's the next stage, is to drill the heatsink, mount the transistors to the heatsink. You've got just these large flat pack transistors and sill washers. So these are fairly large transistors, but yeah, they're not using any isolation. What's the word I'm looking for? Bushings that go on the screw there. Technically, because this end or this side is a plastic material and it's not contacting this metal area here directly, you shouldn't really need one, as long as when you get your sill washer that you've got it dead center and you're using the correct size screw, which is an M3, and yeah, it's not cockeyed or anything. It should still work okay. They've also given me a variety of different screws. They've given me flat heads and Phillips heads. There's a flat head, another flat head. So all these screws are all different types, which is annoying on an output stage when they're all different screw heads. So I'm going to use my own screws and keep them all Phillips head. Anyhow, moving on. Right, so that's the heatsink all drilled and tapped to 3mm. So now all I need to do is start mounting the transistors and make sure I've got the right ones in the right place. This is a MJ2119 which goes on this side. So all I need is the sill washer and component. and a screw that's preferably long enough. Now, I was going to use a 10mm. I'm not sure if that's going to be anywhere near long enough. Should be. Okay, so I think it would be easier to mount the transistors to the heatsink with the isolation washers first before the PCB. So that's how I'm going to do it. And for these smaller transistors, I'm using 5mm screws, or 6mm, however long they are. Now, there we go there. So we're going to make sure that we have no continuity between the screw and the collector, which is the center pin of each of these transistors. Actually, we'll check all pins. No continuity, no continuity, no continuity, nothing, 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 nothing. So all these transistors are isolated from the heatsink. Now comes the fun task of marrying it up to the board and soldering it in, but I might put 10mm standoffs in these mounting holes here, because I'm going to make it so that it's well, sitting on the desk. I found the easiest way was to take these small transistors back off, because they're going to have to be bent to fit anyway. So I found doing the larger ones first and then getting the board square with the heatsink and then soldering the center pins of the larger transistors is a lot easier. Although I might have backed myself into a corner here, but you see how well I can just tighten it, so that's alright. And these ones aren't soldered yet, I'm just getting them prepared first. Now I just want to make sure that that is relatively flat. There's a piece of crap stuck in one of these grooves. Don't know what it is, but anyway. Okay, now go along and solder all the leads of the transistors. May take a little bit more heat on some of the pins than others because it is attached to a heatsink now. So, but this soldering iron I'm using is about equivalent of a 40-watt iron, so there's plenty of heat here. I did buy myself a new one, and I made basically a review of it in another video which has not been released. I haven't finished editing it yet because mainly I couldn't well, I couldn't be bothered editing it and secondly the project that I was soldering, I couldn't figure out how to make it work properly. It does work, but it's confusing. So that's the reason why it hasn't been released. And it's not a Chinese kit, it's another silicon chip article. But I may, in the near distant future, finish editing that video off and upload it. And oh, by the way, the center transistor here, which I believe is the VBE multiplier, the holes on those pads were too small too. They were still 0.8, I had to drill them out to 1mm. So that was another annoyance. Some of the holes on this board are not drilled to the correct size. And there's also another slight issue which I don't know if I've already mentioned, but they don't supply enough PCB pins. You need an extra 4 in order to put 2 each fuse holder side for the 560 ohm resistors. And they haven't supplied them. So that's the reason why they're not in there, because I don't have any. And I've lost me ply, not me pliers, me side cutters somewhere. There they are. So I'll just trim off the excess lead. I should say leads because it's plural. And that is the output stage done. Just need to get all these bits of crap. There we go. So that's the output stage done. Nice. So we're almost ready for testing. Now, just reading their recommended construction guide time it takes to assemble this, they reckon 60 minutes. Well, I've spent the best part of 3 hours doing this. I started at, I think it was about 10 o'clock, near about 10 o'clock. It's now 1 o'clock, so that's 3 hours. And that includes drilling and tapping the heatsink, which is the hardest part and the most time consuming. Because you got to, with these miniature taps, you've got to be very, very careful and go slow and steady with it, or you will break the tap. As I discovered when I was doing this heatsink for the other Amplifier project, the tap is still broken off in the hole. And I tried to drill it out with the 2mm drill bit, and that's how the 2mm drill bit is now blunt. However, the mistakes I made with this, and I found this out the hard way, was one, these are only 2mm holes. They should have been at least 2.5. Secondly, I decided to stick the tap into an electric drill to make it go faster, and then it binded because it hit up against one of these fins on the inside and snapped it. And that was the end of that tap. Luckily I had a spare one, but those are the do's and don'ts of tapping heatsinks and material like this. Slow and steady, do not use an electric drill to do it, and make sure your measurements are pretty bang on accurate and not hitting up against fins like this, because you will break the tap. Just saying. Okay, I'm half set up. I've got the power supply on at least. It's set to 0 volts. Now the first thing I'm going to do is power it up, slowly increase the voltage, watch the current. I've got it set on a current limit of about 1 amp. So if it suddenly shoots up to 1 amp, I know there is a problem somewhere in the circuit and I can turn it off. I've got the resistors sort of like bodged into the fuse holders. These basically act as current limiting as well. So we'll apply the load and slowly wind the voltage up. We're at 1 volt, 2, 3, we're about 20 mA, disappeared again, 20 mA, and we're sitting steady at 20 mA, and we're now at 20 volts. So before I go any further, the next thing we need to do is measure the DC offset on the speaker connections after I untwist my leads. And it shouldn't be any higher according to the instructions than plus minus 55 volt. So I'll try and do this out of camera shot, well, me out of camera shot as possible. We have 20 millivolt on the output, so well within the plus minus 55. So without pulling the circuit board off the table, I'll increase the voltage up to as high as the power supply will go, which is 30 volt, and I'll take the current limiting off now because I know it's not drawing excessive amounts of current. I will again measure the DC offset, and we still have 20 millivolts, so that's fine. Now I'm just going to do a little heat check here. Nothing appears to be getting overly hot, so the amplifier is not oscillating yet. So next thing to do is to adjust the bias. Now we'll need to connect across one of these resistors and adjust that potentiometer until we have about 14 volt. Now because I'm running at least 20 volts lower than the recommended supply voltage, we may not be able to get to 14 volt. See, the thing is, it should be a little bit less, yes, because the voltage is less for the quiescent current. You can measure it on an oscilloscope anyway, and you have the thing going up to almost the onset of clipping, and then you adjust this pot until you can see the crossover distortion, and then back it up a bit until the crossover distortion goes away, and then take your measurement there of what your voltage is. But so I'm just going to hook up some test leads across one of these resistors. Now we want to adjust this trim pot, which I'm just doing now. The voltage is now increasing, so I'm going to keep going up until we get close to 14 volt, which is there. Just doing a heat check. These are getting slightly warm, that's fine. So at 14 volts on this pot, each output transistor, well, on this side, is having the effective current through both of these at 25 mA roughly, or 12.5 this device, 12.5 that device, theoretically speaking. So I need to let that sit for at least 10 minutes. Okay, that's been running for about a good 5 minutes now, and it's remaining roughly stable around 14 volt. I did drop it down slightly. Seems to be decreasing as I speak, but yeah, that's pretty much in the ballpark of where we need to be. Do another heat test here. These things are getting reasonably warm. The main heatsink is cold. The resistor is slightly warm. That one's cold. I might be detecting heat from the heatsink actually. I might be confusing my test here. No, that resistor is cold. That resistor is cold. Okay, so now I just want to carefully check the DC offset at the output again. Just make sure it's within spec. So I'll connect my fly leads up to the output terminals. Go back to the millivolt scale, and yeah, still at 20 millivolt. Okay, so now I can turn off the amplifier, and I can remove these 560 ohm resistors if I can, like that, and now pop in the actual 5 amp provided fuses, which is ordinary slow blow, fast blow rather. Plug them into the clips. And for a kit that's been sitting around for God knows how many years, and the components as well, seems to be working reasonably well. So we'll ignore that. And with the power applied, we're still at roughly 20 millivolt. Everything's starting to stabilize as the capacitors charge and whatnot. And we are at about 20.9 millivolt, and the current's going back and forth between 40 and 50 millivolt. Sorry about that. Now we're at 21 millivolt and increasing. Just going to do a heat test here. Yeah, it's hovering around 21 millivolts, so that's fine. So now I'm ready to hook it up to a resistive dummy load and oscilloscope and function generator, and yeah, we'll see what its results are. So let's turn it on and see if we get anything out on the scope. And yes, we do. We get a reasonable signal. I'll just adjust the trigger so we can see it. There we go. Now currently we're at 5 volt per division, so I'll drop that down to 1. And now we can see we're getting 27.9 volt peak to peak on that. So is that at clipping? I'm not too sure. So I'm just going to do a quick heat test on the output devices, and they are starting to warm up. So let's increase the amplitude of the DDS until it starts to clip. Keep going, keep going. No, not yet. Oh, we're flat topping in there, so back him off. We're currently at 1.9 volt peak to peak input, and that's giving us roughly 40.5 output. We're drawing close to an amp, so that's reasonable. So we got 40.9 volt, and we square, that's peak to peak, so we need to halve that. It's about 20 volt, so 20.45, so that's easy to do. 20.45, we square that, which equals that, and then we divide that by the resistive load of 8 ohms, and we get roughly 52 watts. So, yeah, nowhere near the 112, but there is a reason for that. We are only operating on plus minus 30 volt. And in fact, the power supply is bogging down to 26 now at full output. So that is the reason why, because the power supply is not high enough. So now I'm going to change to the sweep function and see how relatively flat the frequency response is. Yeah, it looks relatively flat to me. Looks quite good actually. Starting to roll off now. That's at full output power. So yeah, the frequency response is pretty good. So I guess now what would be a good idea is to actually now hook it up to a source of music and a speaker and actually hear what the thing sounds like. Now I'm going to use the laptop again as well because it's convenient, and plus I can control the volume via the volume control on the computer. Now I'm just going to get set up for that. I'm going to put away the DDS and the oscilloscope now. Okay, well that's all set up to a speaker now and source of input. So now I can turn the amplifier on. I heard a slight pop. Let me just disconnect the input lead for a second. Yep, that's working. Okay. Now I've got the audio level set to about 1. About 15 is enough, I think. It's only coming out the one speaker, obviously. So I'm just going to go into here and play a track. My left ear is lonely. Yes, that sounded pretty nice. And that's just that flat response. There's no bass increase or treble increase. It's just running normally at flat response. It was well worth the $45, I think it was, I paid for it on eBay. I'll post a link in the description to the kit. Remember that these are old, very old stock, and they've been sitting around a long time, so you may have a little bit of difficulty soldering to some components, just saying. But yeah, I'll put a link in there, and if anyone wants to buy one, I believe you can buy it from interstate as well. It doesn't really matter, like overseas, I mean, not interstate, because the warehouse for Jaycar is in Sydney. That's where it comes from. But people in America and Canada and China or wherever else you might be watching this video right now, you should be able to, via eBay at least, order one and they'll send it to you. Yeah, but all in all, I'm happy with the response of the amplifier. The output wattage is reasonable for the voltage it's running on. Now, the question you may be asking yourselves, what is he intending to do with it? Well, I've got another project in mind, which is a little bit more less involved than the previous amplifier I built is, and you'll see in upcoming videos where I'm going with it. But I'm going to leave that up to your own imagination, and you can comment below if you like with suggestions of what I might be doing with it, and I'm not going to say either way yes or no. So anyway, I hope you enjoyed this video. Thank you for watching, and remember to give it a big thumbs up, and yeah, I'll catch you in another video. See you later.